Welcome everyone to this week's Oregon Minute. As you can see, we are still doing our interviews from home and over Zoom for the time being as COVID-19 cases continue to rise in the county and in the rest of the state. And speaking of COVID-19, we are actually interviewing Robert Kirchdoerfer today, who is an assistant professor at the University of Wisconsin Madison and the Department of Biochemistry there, as well as the Institute for Chemical Virology. And Robert happens to be Tom Kirchdoerfer's son, who has been very active in the Oregon community. So welcome, Robert.
Thank you so much for having me.
So, Robert, you grew up in Oregon, and as I just mentioned, your father, Tom, has been very active in the community. What were some lessons that you learned from him, and what was your experience growing up here in Oregon, as well as having someone like Tom as your father?
My experience was great in Oregon. I loved growing up in Oregon. I had a lot of extracurricular activities growing up. Was a very active participant in the local swim team. And I also participated in Destination Imagination, which is a creative problem-solving program run through the school district. And really what I think that these things really emphasized to me were how important hard work is and really sticking with something. Nothing in life, it really works out to be easy if you want to be good at it. And really, I think that these experiences really taught me to, persevere and get better at these activities, which is something I've definitely carried forward. In terms of things I've definitely learned from my parents, and I'm sure that they're watching this, is really that, as good as you can do today, you can do even better tomorrow. And so you never really give up trying to make either the world or what you're doing just a little bit better. So those, I would say, are the really important lessons that have carried me through.
So then what about, because the Oregon community really values its school district, and I've gotten to see some of it for myself in action, just how much time and effort the teachers and school staff really put into their students. At what point during your education here in Oregon did you decide that you wanted, or maybe it was after you graduated high school here or in Oregon, at what point did you decide you wanted to venture into the field of biochemistry, biology, things like that?
So I took to science pretty early. I've wanted to be a scientist, I think, since the 4th grade, and kind of followed that path all the way through. I started out wanting to be a marine biologist, and then suddenly decided that I was really interested in genetics, and I was going to learn everything about heritability and recombinant expressions and genetically modified organisms, and I was just really excited about that. And that really carried me through high school as a goal and something I wanted to do with my life, is to do science. And then when I got to college, I learned a lot more about biochemistry, and that's really where my more molecular studies, which are more recent, have really started to take off.
Give me a little bit of your background and what led up to your position being an assistant professor now and playing a major role in vaccine development for the COVID-19 pandemic.
Sure. So no path through life is a straight one. When I went to University of Wisconsin Madison and got a double major in biochemistry and genetics. And while I was here, I really started to get involved with undergraduate research. So this was working part-time in a lab in the chemistry department, looking at protein folding. And while I loved my research project, I would spend long hours in the lab working on this. for me, it wasn't distinct enough. At the end of the day, you'd get a bar graph explaining what your data meant. And I really wanted something much more high resolution. I really wanted to see the proteins that I was working on.
If I can back you up for a second, what is protein folding? Because based
Sure.
on our conversation before we started filming, I feel like protein folding might have something to do with when we get to the portion where we talk about your COVID-19 research and everything.
Yeah. So basically, the idea is you have a bunch of, you can think of them as a bunch of beads that are strung together. And so each of those beads is an amino acid. Those are your basic building blocks for making protein. And your DNA encodes a specific sequence that gets turned into another sequence of amino acids. And so when we say the DNA encodes information, that's the sort of information it's encoding, is it's encoding protein sequences. Once that protein sequence gets made, and it's just this long chain of amino acids, what winds up happening is that long chain folds into a complex three-dimensional structure. And it's that structure and chemistry that imparts the function to the protein.
That's really interesting. So then you, having gotten up to being the assistant professor at UW-Madison, your alma mater, you have, as I mentioned before, played a very significant role in both the research of COVID-19 and the development of a vaccine. So can you take me through some of the research you did back in like 2015, 2016 at Scripps Research Institute? Because as far as I understand, you worked in San Diego for a time doing research on coronaviruses before coming to UW-Madison.
Yeah. So my research in San Diego at the Scripps Research Institute, it really kind of spanned a lot of different viruses. And I started off in influenza, and I moved to Ebola, and I finally found my way into coronaviruses. What we were really interested in coronaviruses was a protein called spike. And the spike protein of coronaviruses sits on the surface of the virus, and it helps the virus bind to host cells and then enter those host cells. And then that initiates the infection of that cell. And when we started this project back in about 2015, we didn't know too much about how the spike protein really folded up into its complex three-dimensional shape. And so we set out with a collaborator, it's Jason McClellan, who was at the time at Dartmouth and has since moved to UT Austin, to use high-resolution imaging, in this case cryo-electron microscopy, to determine the structure, the three-dimensional structure of the coronavirus spike protein. Our initial studies were done with a virus called HKU1. This is a human coronavirus that typically causes common cold-like symptoms. And then we repeated those findings with the original SARS virus as well as MERS coronavirus. One of the challenges that we had in working with these proteins is that to be really functional, a protein also has to be dynamic. So a protein is not just a static three-dimensional structure. They're always flexing and moving. In the case of spike, they undergo these large shape changes. And that's part of their function to enter cells. In this case, we really wanted to encourage the protein to adopt a particular shape. And so when your immune system sees a virus, it recognizes particular forms of proteins. In this case, the relative or the relevant shape of the spike protein is called the pre-fusion form. And then throughout the virus life cycle, it transitions to a post-fusion form. But if we wanted to make antibodies against spike, we want those antibodies to target the pre-fusion form. Now, whereas HKU1 spike was really well behaved, when we started working on other coronavirus spikes like SARS, the original SARS coronavirus, and MERS coronavirus spikes, those were much more unstable. They tended to undergo these large shape changes spontaneously. And so our collaborators, Jason McClellan, designed two mutations in the viral spike protein based on our high resolution structure work to keep the spike in that initial pre-fusion conformation that is going to be ideal for presenting to the immune system to make antibodies. These so-called 2P mutations have now been incorporated into the spike vaccines that are being used by both Pfizer and Moderna.
And that was going to lead into my next question, is that, what, as much as researchers, because of the emergence of SARS, we had that in 2002, and then I think it was it 2012 we had MERS. They predicted based on those outbreaks that there might be a novel coronavirus, maybe not pandemic, but at least an epidemic, based on that research. But so I would imagine when you were doing this research, you knew that eventually maybe it could inform research about a novel coronavirus at some point. But I would imagine no one could have predicted that it was going to be a pandemic of this scale.
No, certainly not.
So,
Yeah, coronaviruses frequently jump into the human population. Most of the time, that doesn't go anywhere. So you've got an animal, it has a coronavirus. That virus tries to jump into humans, but it can't make any headway, and it just disappears. So emerging viruses, the human population is constantly being challenged with new viruses. And it's really just an unlucky roll of the dice that we wound up with something like SARS-CoV-2 that causes COVID-19. But again, if you roll the dice enough, eventually one of those perfect storm situations do come up.
And in this instance, and it was a wet market in Wuhan, China, and then it was the virus jumped from a bat to a pangolin and then to a human, as far as I understand. That's as far as I understand.
It's a controversial hypothesis. It's definitely probably true that the SARS coronavirus 2, the causative agent of COVID-19, has a bat origin. In other coronavirus outbreaks, we've seen coronaviruses jump from bats to an intermediate species and then into humans. In the case of the original SARS coronavirus, that was the Asian palm civet, which is kind of a cat-like raccoon animal in Southeast Asia. And in case of MERS coronavirus, it's camels. For SARS coronavirus 2, we don't actually know what the intermediate species is. There was some suggestion that it could be pangolins, but this was based on limited sequencing data, and further sequencing data seems to suggest that that's not a likely carrier. At this point, because there is so much SARS coronavirus 2 in the environment, there's just so many cases and so many people, it's likely that we might never know what or if an intermediate species might have been kind of a carrier for SARS-CoV-2.
And I appreciate your clarification on that. So I want to go back to talking about the actual spike protein of the virus and try to kind of simplify that a little bit for our viewers. So the way that I interpret that in some of the reading I've done, so the spike protein attaches, or it unlocks. What I've heard is that it kind of like unlocks your cell like a key, and that I don't know if the inject is the right word to use, but it injects its own, RNA, I believe, into the cell, and then it destroys the cell and then it like multiplies that way. And so when you say stabilizing that spike protein, what you're doing is you're preventing that key from slipping into that lock. Is that a pretty good visual tool, a visualization?
It is. So, I mean, it's important to draw the distinction between the spike on the surface of a virus and the spikes that are being used in vaccines. So the purpose of a spike on a virus surface is to enter cells. And like you said, it's unlocking a door. And in that case, the spike has to carry out a lot of functions. It's involved with a lot of host factors. It involves a membrane fusion activity. This is all really, really important. But for vaccines, what's really important is that you present a surface, a protein surface, that looks like the authentic spike. And it's those authentic surfaces that are going to be targeted by your immune system to make antibodies. And then those antibodies that bound to the vaccine piece can then go and bind the authentic spike. So in this case, our designed, our stabilized spike is not capable of unlocking that door. It's actually been inactivated, so it cannot do that. But it's also not attached to a virus, so that's not really that relevant. But it does present the correct surfaces for antibody recognition.
So how does it impact you knowing that, this research, both, the COVID-19 research the university has done in general, and then this research you did back in 2015, 2016, how does it feel knowing that now plays a role in two, not one, but two vaccines that are likely going to be disseminated out into the public? They're 95% effective. I know Pfizer said 90%, and then they backtracked and said, no, it's actually 94 point, something percent. But how does that impact you knowing that, you and your team of collaborators played a role in this effort?
It feels amazing. To be able to do basic science is a gift. I get to go into the lab every day, and I learned new things that no one has ever seen before. And I think that when we try and examine our motivations for why we do science, yes, we do have that thrill of discovery, but to be able to help someone, I think is really important, and it's very rewarding for us.
So then how both vaccines, how do we kind of touched on this a little bit before I asked that previous question, but how exactly do these vaccines work in helping to provoke an immune response in humans?
Sure. So the way that your immune system works is it goes around looking for things that it identifies as not you. So we call them non-self. You have something called immune surveillance. And so what a vaccine does is it introduces something that is non-self. That gets seen by the immune system. The immune system mounts an immune response, and that generates T cells and antibodies to bind and inactivate the incoming non-self part. The current vaccine is a little unconventional from probably a lot of vaccines that people have had. It's actually an mRNA vaccine, whereas traditionally vaccines have been either a purified component of a virus or maybe a heat inactivated virus. This is going to be like the flu shot that you get every year. The current vaccine is what's called an RNA vaccine. And so in the cell, RNA is used as a message to make proteins. And so in this case, what you're being injected with is an RNA that encodes a protein. So that RNA is going to go into your cells. Your cells are going to read the RNA and make the protein, and then they'll display that protein on the cell surface. And then that will be the target for T cells and antibodies.
So that is so interesting. So then, what do you have to say to those? This pandemic has been, and I'm sure you are aware, a controversial one. We have people who feel that even something as trivial, I'll use that word, as wearing a mask. We have people who believe that coronavirus isn't real. What do you have to say to those people and then those who might be afraid to take this vaccine once it's disseminated?
So one of the things that happened once the pandemic started was we saw the incredible politicization of the pandemic, which I think is really unfortunate. This didn't need to be a political event. It shouldn't be a political statement whether or not you wear a mask or listen to public health officials. These people are really there to safeguard the population. This isn't done to restrict your freedoms or anything like that. This is really done for the public good. And while you might not be in a high-risk group for dying of coronavirus, that doesn't mean that your neighbor isn't. And so certainly the way that I approach wearing masks, and I will tell you, I don't care to wear a mask. If I can get away with not wearing a mask, I don't wear one. But I decided a long time ago that I was not going to be part of the problem, that I wanted to be part of the solution. And so I wear a mask every time I go out in public, especially in enclosed spaces. I'm at work now. I wear a mask as soon as I leave my office. We also do a lot of hand washing, a lot of decontamination. And that's just general workplace things. That's not specific to our research or the work that we do. This is something that I think a lot of people are facing. And so coronavirus is very, very real. You only really have to look at the hospital statistics to see that. The number of hospital admissions just keeps going up and up and up. In terms of whether or not you decide to get the vaccine, again, this is like wearing a mask. It is a way of protecting not only yourself, but your family and your neighbors, especially those who are at risk for more severe complications. That includes the elderly, those who are immune compromised, those who are pregnant, cancer patients. All of these people either can't get a vaccine or the vaccine won't be as effective for them. And in this case, you're helping them. So this is a little bit of playing off of making I don't want to call it a sacrifice because I don't think it's a sacrifice to get a vaccine, but making a choice to support your community. And so that's what I would say to people who are hesitant about getting this vaccine.
Are there, and that leads me to ask, are there any side effects that come with the vaccine? I've read they're similar to the flu vaccine. And then another, how often does,
Emily,
do
you still there?
researchers envision people taking this vaccine? I hear that it's like 2 doses, but then is this something that they envision like annually, or is that not known yet?
So the 2 doses, I think it's 2 doses a couple of weeks apart. There are so every vaccine, every drug, it doesn't matter what it is, there's always side effects. In this case, the side effects are going to be pretty mild. So you get your flu shot and then your arm hurts for a few days. That's basically what we're looking at with these sorts of side effects. I know of no strong adverse reactions to this particular shot or to these particular shots, and it is incredibly effective. So I think, yeah, it's definitely not infective. There's no live virus in these vaccines, so you cannot get coronavirus from the shot. Don't believe that for a second.
I'm not sure if is this something that I'll just repeat this one more time. Is this something that they anticipate annually, or is it kind of a one and done deal? You get the polio vaccine or chicken pox or something along those
lines. So the short answer is we don't know. One of the disadvantages to having clinical trials that are this short is that we don't know the long-term efficacy of the vaccine. And it's just not possible to say, in 1 year, how the vaccines or how your immunity is going to look in 5 years. I think that what we've seen in the past with coronavirus infections is that immunity does tend to decrease over time. Whether or not that decreases to a point where you're no longer protected isn't clear. I would guess, though, that even if you are no longer protected from disease, you might still be protected from severe disease. But that's very, very hypothetical right now. I think that we could be looking at a situation where you might have to get a shot every year. But again, we're going to have to wait and see how durable that immunity really is.
Yeah, and it's amazing to me what we know now about the novel coronavirus in general versus, how we knew absolutely nothing back when it first. That was a year ago now that it started circulating through the world. Um, so then we talked about wearing masks already. I think at this point that's a pretty obvious way to help prevent the spread. But as we wait for public distribution of these vaccines, um, and as a health expert, what are things that people can do right now to protect themselves and their loved ones, especially during the holiday season?
My number one piece of advice is don't be complacent. Yes, we do have a vaccine now, but it's going to take a long time, several months, I would guess, until we can vaccinate enough people that COVID's not going to be a problem anymore. So don't think that just because we have a vaccine on the way, that we can just let loose on all of these restrictions that we've had for the last 9 months. This problem is still here, and it will still be here for quite a while yet. In terms of what we can do for the holidays are going to look different. And as someone who loves the holidays, that hurts me in my heart. I can't hang out with my nieces and nephews this Christmas. But again, this is doing what is best for the community. And I think that actually, really embraces the spirit of the holidays. Giving to others and doing really what's best for the community. That's going to involve probably socially distanced, gatherings. So, you want to sit on one side of the driveway, I'll sit on the other side of the driveway. Wear your masks when you go to the grocery store. Traveling is not a good idea during a coronavirus pandemic or any kind of public health emergency. You should be really conscientious of self-monitoring for symptoms. Did I wake up with this cough? Do I have a sore throat? Am I running a fever? And if so, make sure you take care of that right away. Self-isolate, contact your doctor right away. The faster you take care of this thing, the better your outcome is going to be in terms of your own health and the fewer people you'll spread it to. So be very proactive in assessing your symptoms and the symptoms of people around you.
Do you have anything else that you would like to add today, Robert?
Not particularly. I wish everybody a happy holidays under the circumstances, and we'll get through this together.
Thank you so much, Robert, for appearing on the show today. And just thank you for all of the work you are doing in general. It has major implications for not just now, but 5 to 10 years in the future as we continue to learn more about COVID. And just thank you to all of the healthcare professionals out there who continue to make major strides in researching this virus and making sure that we remain safe in general. So with that, I will say thank you for viewing today's Oregon Minute. And as always, tune in every Thursday at 7 p.m.